Welcome back to this second day of the talk and the last of this four lecture series. So, uh, Professor Mahan will talk about hyperbolic geometry and chaos in the complex plane. And I think he will also explain Cannon-Thurston maps. It's an area, it's a topic for which Mahan Maharaj is very famous for his work. So over to you, Mahan.
Great. Thanks a lot, Mainak. And I think I alluded to this connection with complex analysis in my previous talk. And here what we'll do is essentially, I think as yesterday, what we did, we basically introduced and provided some formalism for the subject in the first talk. And in the second talk, what we'll do is some part of the talk will be general motivation, and we'll be answering one of the questions that came up. Essentially, is hyperbolic geometry just something abstract, or does it have really rather concrete applications? And the answer will be affirmative. There are very concrete applications. But from a general, instead of a general motivation, after a general motivation, we'll be basically talking about what are the kind of things that it has led to within mathematics, and I'll give some instances. So yeah, it's definitely an area which is a topic of considerable current interest, and so we'll try to do that, both outside of mathematics and within mathematics. Okay, good. And here is, I think this is Thurston's name had come up yesterday. In its modern incarnation, in its connection to low-dimensional topology, this is the person who set out the whole thing, Fields Medalist from 1983, and this is one of his beautiful comments. The best mathematics uses the whole mind, embraces human sensibility, and is not at all limited to the small portion of our brains that calculates and manipulates symbols. Through pursuing beauty, we find truth, and where we find truth, we discover incredible beauty. I should mention one thing, that I was there at the last talk that he gave in 2012, few months before he died. He was just recovered from a severe surgery because he was suffering from a rare form of skin cancer, melanoma. One eye had been removed. He was not able to speak clearly or enunciate clearly. And in spite of all that, he gave a 1-hour talk. He had proved, after coming out of his cancer, he had proved a rather fundamental theorem that year. And he gave this fantastic talk. And it is a kind of a swan song. And none of his physical ailments were visible during the talk. You could see him that he's lost an eye. His scalp was covered with sticking plaster, essentially because the skin was affected. But anyway, that's how it is. It's an incredible courage and that's what real deep absorption in mathematics gives you. Very inspiring for all of us. Okay, so with that little bit of spiel in place, let me just say what exactly is hyperbolic geometry just something abstract, some axiomatic system, or is there something very natural associated with it? And here's the basic point. The intrinsic geometry of trees around us is hyperbolic. So basically what we are trying to say is that you have these branches dividing up and further dividing, and then finally you get to these leaves, which is some kind of a crinkly structure at the top. A similar thing happens on the roots. There is a physical problem that the tree is trying to solve. What the leaves are doing, they're trying to, the tree is trying to solve the problem through its leaves of maximizing surface area so that it gains maximum amount of light. Yeah. That's what is going to give rise to photosynthesis. It's going to give rise to food for the tree. Similarly, what the roots are doing is it's basically trying to divide below so that it gains a maximum amount of surface area to absorb the largest amount of water possible. Again, it's trying to maximize surface area for consumption of water. Whenever there is a problem, a physical system tries to solve a problem of maximization of surface area. See, when something tries to minimize surface area, the geometry that results is spherical. Yeah. So water droplets, they try to minimize surface tension. So they try to minimize surface area. And that's what gives rise to these water, these round bubbles, yeah? Round droplets of water. But when a system, physical system, in this case, the tree, when it tries to maximize surface area, when that problem is trying to be solved, the natural geometry that results, the natural intrinsic geometry that results is hyperbolic. I mean, it's a name. Hyperbolic is a name, and we'll try to figure out what exactly are the features of this geometry as we go along in this talk. And this particular thing is quite easily visible. So we strip away from that tree the extra structure of the leaves, and then we have this tree where you can see that the branches are multiplying, and at each stage there are more and more connections developing, and as it's reaching out towards the sky. If we strip away further structure and try to put a mathematical thing on it, this is still artistic. What you see is that at each point there's a branching with degree 3. Yeah. And then as you go out further and further, towards the end, you see things which start looking like leaves. Now, make it a little less picturesque, a little less artistic. And then you have exactly the same tree, the regular three-valent tree. A tree means it's a graph now, where there are no loops. Yeah? And all the edges are typically thought of as having the same length, but we can't. I'll draw your attention to this one feature. If you try to embed a tree in this Euclidean flat plane, then in order to embed that tree as you go further and further out, the lengths have to be shrunk in order for you to actually draw a faithful picture. What happens in Euclidean space with natural trees is exactly the same thing. This is the reason that branches, the size of branches, become smaller and smaller as you go away from the stem. Yeah. Why? The intrinsic geometry of the tree, which is hyperbolic, is fighting with the ambient geometry, the geometry of the ambient space, which is Euclidean. There is an incompatibility between these geometries. If a tree started growing in hyperbolic 3 space, for instance, it would not have to shrink its branches, except for the physical constraint of having to support a load. The geometry would not constrain the geometry of the ambient space would not constrain the geometry of the tree. Yeah, but in Euclidean space, the flat Euclidean metric outside is in contradiction with the intrinsic geometry of the tree, which is why you see this kind of a feature. But now let's go to a purely mathematical description of the intrinsic geometry of the tree without an external Euclidean constraint. So what is it? It's just a graph, and there are these vertices which are given by these black blobs. Remember the matchstick figures that we drew yesterday?
Can I interrupt you? There is a
Yeah, sure.
question.
Yeah.
What is the geometry of the universe, or is it geometry-less?
Geometry is really the way human beings try to understand the universe. Yeah. Is there a universe without one's understanding of it? It'll drag us into all kinds of silly philosophical questions, and I don't want to get into any kind of philosophical ideology. I mean, it's so it's really, I mean, so I think, is there a geometry of the universe? The precise form of that question should be, is there a geometry in our human understanding of the universe? Answer is emphatically yes. So here is the point. And what is the geometry of the universe? We know the local geometry of the universe is three-dimensional. And what are all possible three-dimensional geometries is a classification problem that we did address yesterday. Okay, good. So now let's return to the geometry of something like a tree. And so here it is. You have these vertices, which are these black blobs. They're connected by edges. All the edges are of the same length, and we normalize it to have length 1. So this is a mathematical representation of a tree. All edges length 1, and there are no loops. Good. So we started with a natural tree, started stripping away structure, and then finally this reduced it to what is a mathematical representation of a tree. So we have to make definitions, and this is the definition we make. Graph without loops, edges of length 1. That makes it into a metric space. But there are other examples beyond trees, and as I said, wherever there is a surface area maximization problem, hyperbolic geometry comes in. So here it is, sea anemone. What it's doing, you'll see that the edge of the, these are like really, it's like slightly fattened discs, and they are trying to absorb nutrients from the surrounding water. So they are trying to maximize surface area, and what's happening is that the boundary of these discs now start looking like these very, very floppy circles which are curving in on themselves. And so this kind of curving in on itself is again a feature of hyperbolic geometry. Yeah. So again, this is a system, a natural system, trying to solve a surface area maximization problem. And at the rim, which is the circle at the boundary of these disks, again, you see a carunculated behavior. This is a phenomenon. This is a universal phenomenon. What happens is that if there is a surface area maximization problem, the edge of the system, in this case, the circle, in the case of a tree, it's the collection of leaves, the foliage at the top, all of them become highly irregular. Yeah? There's a mathematical structure underlying it. We'll come to that very soon. But that occurs in our brains. Brains, what are they trying to do?
Mahan, can we define metric on tree?
Yeah. So that's what I said. So each edge has length 1. So what is going to be the metric that is the different distance between 2 points? You look at the edge, all collections of edge parts from the first vertex to the final vertex, and then you look at lengths. Yeah. So then the minimum of all those lengths is going to be the metric. What is it? It's going to be the count of the smallest number of edges in an edge path traveling from one vertex to another. Good question. Here is another natural phenomenon, the surface of the human brain, and it's also trying to solve a surface area maximization problem by trying to divide up. And if you look at the local phenomenon, a neuron, the tip of the neuron has many connections. And wherever there are many connections, the surface area is going to be carunculated like this. Yeah. So the surface of the brain, again, is a result. There's a 2-dimensional surface bounding a 3-dimensional geometry, namely the neurons multiplying and dividing. And the surface is carunculated. The internal geometry is hyperbolic. Again, surfaces of cauliflowers and so on. Yeah, so natural phenomena so hyperbolic geometry is something which is a very, very natural phenomena, and it arises very often. The internet, with its vast connectivity, is actually a local model for that. The best would be hyperbolic. Yeah. Go back to this aesthetic representation of a tree. And now I will get into mathematics per se. And this is a picture from a book called Indra's Pearls by David Mumford, David Wright, and Caroline Series. And it looks like a collection of emeralds. Yeah. The blue stuff on the back, you should think of that as a complex plane. And this collection, almost like a very ornate ornament. Yeah. This collection of jewels is essentially stuff that is put together, and it gives you a beautiful design. Yeah. And it's a structure that keeps replicating at various scales. Yeah? And as we go on, this picture, essentially think of a three-dimensional space sitting over the blue flat plane that is there on the screen. The blue flat plane is complex, and the geometry of the space that hits it from say, outside the plane onto it is really hyperbolic 3 space. What is hyperbolic 3 space? We discussed the hyperbolic plane in the previous lecture. Its metric was ds square equal to dx square plus dy square by y square. And here is just that same thing raised one dimension. It's ds square equal to dx square plus dy square plus dz square, whole thing divided by z square. Yeah. And so this is the three-dimensional hyperbolic geometry. And this picture is basically an encapsulated form of saying that, well, in this three-dimensional geometry, I mean, these round things that you see, they are actually two-dimensional analogs of these semicircles. They are basically hemispheres which intersect the boundary complex plane at right angles. Yeah, the dihedral angle is constant 90 degrees. So this is really the three-dimensional version of the hyperbolic plane that we introduced last time. The hemispheres, this is these round jewels that you see, they are the analog of the two-dimensional analogs of these semicircles. Yeah, you take the surface of revolution of a semicircle, you get a hemisphere. Yeah. So this picture encapsulates the title of the talk, yeah, which is hyperbolic geometry, which is a three-dimensional thing in the space that hits the plane. And the complex plane is the blue thing. And there you have a dynamical picture which gives rise to chaos. We'll return to that issue. And that's going to be the main mathematical content of the talk now. Good. So now let's return to this question and define precisely what is a hyperbolic metric space. Firstly, it's a metric space, which means there is a way of measuring distances between points which satisfy the usual notions of axioms of a metric. Yeah, symmetry, reflexivity, and transitivity, right? Along with this thing that dxy is equal to 0 if and only if x is equal to y. Okay, good. The key feature, the key large-scale feature of metric spaces, which defines hyperbolicity, is thinness of triangles. What does it mean? That you now assume that any pair of points, so now for the rest of the talk, we'll not just think of spaces equipped with a metric like ds square equal to dx square plus dy square by y square, or ds square equal to dx square plus dy square plus dz square by z square, but also graphs. Yeah, graphs where all edges are of length 1 and the distance between 2 points is given by the shortest edge path, the smallest number of edges, tail to head, which connects two vertices. So what is thinness of triangles? It basically says that you take any shortest path, which we will call a geodesic AB, and then that is contained in the delta neighborhood. So take any 3 points, A, B, and C, and then you can construct a triangle in this generalized sense. What is a triangle? You take any 3 points, A, B, and C, join A and B by a geodesic or an edge path, join A and C by a geodesic or an edge path, AC, and join B and C by a geodesic or an edge path, BC. Thinness of triangles basically says that there is some fixed delta greater than 0, such that every side is contained in the delta neighborhood of the union of the other 2 sides. So in this tree, it's easy to check that delta is actually equal to 0. Why? Because then what does a triangle look like? You take any 3 points on this tree, and then what will happen is that there will be 1 point which lies outside the shortest path joining, say, A and B. And then the shortest path from this 3rd point, C, is going to come and hit this geodesic AB at a point, and then is going to follow either path along this geodesic to A or the path along this geodesic to B, which means that a geodesic triangle in a tree looks exactly like a tripod. Yeah, there's a point in the middle, and then there are these three limbs hanging off it. Yeah, so which means that AB, a side of the triangle, is actually contained in the union of the other two sides. It's contained in AC union BC, which is exactly the zero neighborhood of AC union BC. So trees are really delta hyperbolic metric spaces where delta is actually equal to zero. So quick summary, what is a hyperbolic metric space? A, it's a geodesic metric space. B, triangles are thin with thinness constant delta fixed for all triangles. What is an example of something which is not hyperbolic? And this is our Euclidean space. See, I said that the Euclidean geometry is flat and the trees are fighting that geometry when they try to maximize surface area. See here, why is the Euclidean geometry not hyperbolic? Well, you give me a delta. See, delta here is typically thought of as large, not as small. Yeah, so delta could be 1,000, delta could be 10,000, whatever. So you give me a number, delta, say, let's say delta equal to 10 million. Yeah. And I'll have to construct for you a geodesic triangle in Euclidean space so that a side is not contained in the 10 million neighborhood of the union of the other two sides. So what do? You take an equilateral triangle whose sides are of length 1,000,000,000. Yeah? Then it's an easy check to see that no side is contained in 1,000,000 neighborhood of the union of the other two sides. That's all there is. And so Euclidean geometry, and this happens for all large values of 1,000,000, billion, etc., etc. You take any large number, the same thing as you just take twice that number and it's going to work. Yeah. So this basically says that flat Euclidean two space is not hyperbolic. And that's the reason why trees are shaped like trees. Geometric reason is that. Good. So now we have defined hyperbolic metric spaces. And now let's revisit what we have said informally before. What happens is that as you try to fit this into R2, the limbs are forced to be shorter and shorter. And then on the boundary, it accumulates to a Cantor set. A Cantor set is something which looks like itself at every scale. Formally, it means that take any point, take a small neighborhood of that, it looks homeomorphic to a macroscopic part of the whole thing. This is called geometry replicating itself at all scales. And this notion, this mathematical notion that formalizes all this is the notion of fractals. So what are we talking about so far? You're looking at hyperbolic geometry in some dimension, let's say n. Then the boundary of that is one dimension less, n minus 1, and it has the structure of a fractal. Yeah? And so this is really the formal mathematical structure that encapsulates all the pictures I showed. The surface of the brain is like a fractal. The inside three-dimensional geometry of the brain is hyperbolic. The one-dimensional geometry of the tree is hyperbolic. Its boundary, like here, is like a zero-dimensional object, the Cantor set. The two-dimensional anemone that we drew, it's like a disk. Its boundary is a fractal circle. So whenever you see a fractal in some dimension in nature, almost invariably it means that there is a one higher dimensional hyperbolic geometry going on, which is leading to that fractal nature. So this is really, this fractal and dynamics on it is exactly what chaos is about in the context of this talk. Yeah. And so the real reason, the real connection between hyperbolic geometry and complex analysis is that geometry in dimension 2 plus 1 gives rise to complex analytic dynamics in one dimension less, which is 2, and that gives rise to chaos. Okay, good. So now we introduce something from dynamics, which is collections of symmetries.
Mahan, there is a
Yes,
question.
yes.
How is boundary defined here?
How is boundary defined here? You look at a path in your space and look at points towards which it is trying to accumulate so that it does not continue beyond. That is the boundary. That's all. Or, I mean, in this particular case, it's the set theoretic boundary. Yeah. You look at it embedded in Euclidean space and just look at the top, I mean, the boundary as a boundary of topological space. Points for which, I mean, essentially there is no, I mean, it's the space closure you intersect the no, that's maybe not the right way. The right way would be to look at paths in the space and look at these guys going off to infinity where they would try to accumulate. Let me get to this particular slide, and I think your question is going to be answered. Yeah. So here we'll actually be looking at boundaries of groups. Yeah. And then I think the notion is going to become much clearer. Yeah. So what is it? So a group is, I mean, so now we are introducing some third kind of structure, namely an algebraic object. So where do groups come from? They are symmetries of objects, typically symmetries of geometric objects. And then there is a graph associated with a group. So what is it? So a group can be represented, so a discrete group, let's say it's given by finitely many generators, which means the elements of the group are words in these finitely many symbols, G1 through Gk, along with their inverses. And there are finitely many relations, R1 through Rs. We construct a graph corresponding to this group, whose vertices are exactly the elements of the group. The edges consist of pairs of elements of the group, such that they differ by one of these generators. Okay? So now let's take the simplest group in some sense. K is equal to 2, S is equal to 0. So this is called the free group on two generators. Yeah. So here we have two generators, because we have just two symbols, let's call them A and B. So then what are words? Words will be given by A, B, A inverse, B, A, B inverse, etc., etc. All that we are requiring is that we are looking at shortest edge paths, so you don't go along a path and retrace it. So all that we require is that A is not followed by A inverse. Such things are called reduced words in the free group. So it's an easy check to see that these edge paths in this infinite four-valent tree, yeah, those are geodesic paths. And what are we asking? So now we are really in a position to answer this question precisely. What is the boundary? The boundary is basically the asymptote classes of geodesics. So two geodesics, if they lie eventually within a bounded distance of each other, we say that those two geodesics are equivalent. So here in the free group is just going to be an infinite edge path where the only restriction is that it's a geodesic edge path, which means there is no edge followed by its own inverse. Yeah, there's no retracing of a path. And then what happens is that this collection of paths, you can code them. So basically, if you move off along A, coded by a 0, if you move off along B, coded by a 1, if you move off along A inverse, coded by a 2, if you code it by B inverse, you code it by a 3. So it's formal symbol 0, 1, 2, 3. Yeah. And then what you're really looking at is that the 0 should not be followed by 2 and 1 should not be followed by 3. Then this collection of geodesics gives you on the infinite sequences, and those infinite sequences code geodesics. And what we are really asking for is what are the ideal endpoints towards which these geodesics converge. Under this equivalence relation, the two geodesics are the same if they are finally at a bounded distance from each other. In the case of a tree, that bound is 0. Yeah. If they are finally coincide, we basically say that they give a single point at infinity. And that point at infinity is basically this Cantor set, which is what we had hinted at in the previous case. And these boundaries are really fractals. Yeah. So what now we have taken away the natural structures that led to all these things, and then we gave rise to this basically gave rise to all these fractal kind of objects. And so essentially these are coded by 0, 1, 2, 3, etc., etc. And this accumulates to this collection of fractals at the end. Good. So the boundaries of hyperbolic groups are fractals. Yeah. This is the relation. There's a geometry, and now there's a lot of extra symmetries given by the group. And when do we say that a group is hyperbolic? It's basically the scaly graph, which is now a geometric object. All edges have length 1. If that graph is hyperbolic according to thinness of triangle, the definition of thinness of triangles, we say that the group is hyperbolic. And then it comes equipped with a boundary. And that boundary is 1 dimension lower, and that has a fractal structure. Now, the point is, a priori, this depends on the choice of the generating set. A fundamental theorem of Gromov, fundamental observation of Gromov basically says that, look, if you have a finitely generated group, which is hyperbolic, and then you change that generating set to a new but finite generating set, and the original guy was hyperbolic with some constant, then the new guy is also going to be hyperbolic with some other constant. Yeah. So hyperbolicity is really a property of the group itself and not the generating set, and so you can really talk about hyperbolicity of groups. Good. So here is another example, a much nicer example, which reflects back on the hyperbolic plane that we discussed in the previous lecture. This is basically the skeleton of the painting by Escher. So what are we doing? We are looking at, we talked about modular groups, I mean the modular group towards the end. This is a variant of the modular group. What you're doing is you're looking at 3 generators, A, B, and C, such that A square equal to identity, B square equal to identity, C square equal to identity. What that means is that A, B, and C denote reflections. So think of one of these small black triangles in the picture, and think of reflections on the 3 sides. The reflections on the 3 sides are these A, B, and C. Yeah. Reflection squared is the identity. Yeah. And then you introduce what happens at the vertices. So AB is now going to be a rotation about, it's a composition of reflections, right? So composition of 2 reflections in 2 intersecting lines is going to give rise to a rotation. Yeah. So the angle where A and B, where the lines along which reflection is A and reflection is B meet, the angle is exactly 90 degrees. So which means the rotation, reflection on A followed by reflection on B, is 2 into 90 degrees, which is 180 degrees. So that means if you square AB, you're going to come back to where you started off with. That's the first relation. AB square is equal to identity. Yeah. Where you have 8 of these triangles, that's where B and C reflections combine. So that's basically a rotation through. So the angle there is basically pi by 4. Yeah, pi by 4, which means the rotation is through pi by 2. So that means 4 times pi by 2 is 2 pi. So BC whole to the power 4 is the relation that you get by rotation at that point. Similarly, there's some place where it's the angle is pi by 12. Sorry, it's pi by 6, 2 pi by 12. And so yeah, so you look at the rotation obtained by reflecting C and A, that's going to be 2 pi by 6. And then so the CA whole to the power 6 is going to be identical. So you now have a group, and the Cayley graph, if you want to draw for this one, you draw the dual graph to this tessellation, this tiling by triangles, where there's a vertex for each triangle and there's an edge for whenever these 2 triangles share an edge. Yeah. And that gives you a graph, and that graph actually gives you basically a Cayley graph of this group G. Yeah. And what is happening? This is a different model. It's called the Poincare disk model. Yeah, it's essentially we had talked about the upper half plane. But you look at R and put in infinity and you make it, that's conformally equivalent to a unit disk in the complex plane. And so the unit disk and the upper half plane are conformally the same. And you pull back the metric, you get the Poincare disk model. And there, this group actually acts by hyperbolic isometries. And what are the angles of the triangle? It's going to be pi by 2, pi by 4, pi by 6. And you look at the sum of the angles, it's strictly less than 2 pi. Yeah, it's strictly less than pi. Yeah, half plus 1/4 plus 1/6 is less than 1. Yeah, that's the point. And so this is a hyperbolic triangle, and this is one of the most symmetric hyperbolic triangles. And so there is this large class of symmetries and discrete symmetries which give rise to very symmetric hyperbolic objects from discrete groups acting on the hyperbolic plane. So this is a generalization of the modular group. Yeah, the modular group is actually what's there. You have 2, 3, and infinity. Yeah, that's the modular group. Here it's 2, 4, 6. Yeah, you can have PQR, and there's a whole collection of numbers that are possible. Okay, good. Here is a painting by Escher. The previous one was a mathematical description, and Maurice Escher, actually drew many of these pictures, and what he's really drawing is an artistic rendition of the hyperbolic plane, and you can see these whitish lines that go from one end to another, and those are meeting the boundary circle at right angles. Those are the geodesics, and you have points where many of these mouths of fishes and tails of fishes come together. That really is a place around which there's a lot of symmetry. So there is 6 of these geodesics which meet, and so you have a rotation of 2 pi by 6 at those points. Yeah, that's correct. 60 degrees is what they're meeting at. Good. So this is an artistic rendition, but now let's go back to the mathematical stuff. And now we are going to address a very specific question. See, in mathematics, once you have an object, you very often try to probe it through structures of objects which sit inside it, sub-objects. So we know what a hyperbolic group is. We've defined it. Yeah, this is all introduced by Gromov in the 80s. But suppose you have a subgroup of a hyperbolic group, which is also hyperbolic. Yeah. So H with its intrinsic metric is hyperbolic, but it is a subgroup. So in a manifold setup, in a geometric setup, what is it? It's basically you have a submanifold of a manifold, and you have a intrinsic geometry of the submanifold, and you have an extrinsic geometry that it inherits from the ambient space it sits in. So suppose you have a hyperbolic subgroup of a hyperbolic. You choose a finite generating set of H extended to a finite generating set of G. That gives rise to an inclusion of the Cayley graphs. And the basic question that we want to ask is, does this inclusion compatibly act at infinity on the boundaries? And the question thus is, does I extend to a continuous map between the fractal boundaries? This generality, the answer is no. There's a theorem due to Baker and Riley from about 10 years back. But a much more classical question, and this is a problem that was posed by Thurston, basically asks, well, suppose you have a hyperbolic group acting by isometries on hyperbolic 3 space. Yeah, as I said, hyperbolic 3 space is just the upper half space. Its metric is given by dx square plus dy square plus dz square by z square. Its boundary is the complex plane union infinity, which is the Riemann sphere. And suppose that the group acts properly by isometries. The group is intrinsically hyperbolic, and it acts on this hyperbolic space. So the intrinsic group has its own boundary. Hyperbolic 3 space has its boundary, which is the 2 sphere. And now we can quotient out the hyperbolic 3 space by this discrete group. And this is where the quotient space really comes in, and you get a manifold. Hyperbolic 3 space quotiented out by a discrete group gives a manifold. What is this quotient space? So for example, this is a basic notion, which is a lovely notion and very useful. So look at R2, act on it by Z plus Z. How does Z plus Z act? The first Z acts by translation by 1 to the right, and the second Z acts by translation by 1 upwards. Yeah, these are the generators. And then what happens is that you have this little square in the middle which tiles under these translations. And so the quotient basically says that you look at all points which lie in the same orbit, which means they are images of a point under this group action. Yeah. So then what happens is that the blue line at the bottom and the blue line at the top of a single fundamental square, which is called a tile, they are going to be translated one to the other. So the quotienting operation is going to identify these two. Similarly, the orange lines, which are vertical, those are going to get identified. So what are you really doing? You're taking a little square, you're identifying the top to the bottom and the left to the right. What you get is really a torus from yesterday's picture. So the quotient of R2 by this group action is the torus. This is what is quotient topology, which had been promised in the abstract. Okay, good. This can be generalized. As soon as you have a group acting by isometries, then you can quotient out the space by this group. So here is an example of the hyperbolic plane again, but now it's not tiled by squares, it's tiled by pentagons, and 4 of those pentagons together give you an octagon. Yeah. And then the opposite sides of the octagon identified together give rise to this genus 2 surface. I had said yesterday in my second talk that all these surfaces of higher genus greater than 1, they admit metrics of constant negative curvature, which means, this is a different way of saying it, they are really quotients of the hyperbolic plane by a discrete group of isometries such that the quotient space is the surface that you got. And this picture here is an illustration of this fact. Take the hyperbolic plane, construct an octagon, tile it by octagons, look at the group of symmetries, quotient out by the group of symmetries, and you get a constant curvature -1 metric on the genus 2 surface. Good. But this is 2 dimensions. Let's go back to the 3-dimensional problem. What do we have? You have a discrete subgroup of the group of Mobius transformations, but now this is Z going to AZ plus B by CZ plus D, where A, B, C, and D are now coefficients. In the hyperbolic plane case, those were real numbers. Now they are complex numbers. But the rest of it is exactly the same. So Mobius transformations, A, B, C, and D, this is the connection to complex analysis. A, B, C, and D, where A, B, C, D are complex numbers. And that's again the projectivized SL2C group. So take 2 cross 2 matrices represented by A, B, C, and D. But then if you multiply the top and bottom, so assume that AD minus BC is equal to 1. But then if you multiply the top and bottom by -1 or +1, you're going to get the same matrix back. So you have to really quotient out by the center of that group, which is the plus minus identity matrix. And that's this group PSL2C. And this is exactly equal to the isometry group, the orientation preserving isometry group of hyperbolic 3 space. And this is exactly an analog of the statement that we said last time in the previous lecture, that the isometry group of hyperbolic 2 plane is PSL2R. Yeah. So now you have a discrete subgroup acting by isometries of hyperbolic 3 space, quotient out. Yeah. And then what you get is a hyperbolic 3 manifold, and there's the feature of that manifold which reflects the group that we started off with. This is called the fundamental group. This is a basic topological invariant of a manifold. And so this group is exactly equal to the deck transformation group of hyperbolic 3 space to start it off with. This is the geometry side of the picture given by its group of symmetries or isometries. The boundary, which is the Riemann sphere, is the ideal boundary. And its Mobius transformation, as we said just some time back, is given by, so the same group now acts on the boundary and by these Mobius transformations. Yeah. So we'll choose generators G1 through Gk by sending it to some special numbers A1Z plus B1 by C1Z plus D1, defining G1, and similarly G2 to Gk. And then that group acts on this compact space C hat. Since it's acting on a compact space and it's an infinite group, it's going to give rise to dynamics. And inside the three space, inside hyperbolic three space, the action is very nice and you can pass to a quotient. So inside you have a quotient hyperbolic three manifold, that's the geometric aspect. On the boundary sphere, you have a dynamical thing, you have a group acting on a sphere. Yeah. Dynamics on the boundary and in one dimension less on the two sphere, and geometry in dimension one higher, which is 3 dimensions. Good. And here is the basic theorem, which I'll state informally first, which says that these two sides of the picture are exactly the same thing. It basically says there is an exact dictionary between the dynamical picture on the compact side, this is the fractal side, and the geometry of the picture in one dimension higher, the geometry of hyperbolic three space. So this is hyperbolic geometry. So there's an exact dictionary between these. Now let's try to, which means basically from one collection, a class of information, you can go to the other, and from the other information, you can come back to this. So how are we going to work with this? So now let's try to make this statement precise, and the rest of the talk in the last 10, 12 minutes is going to try to make this statement a little more precise. I don't think there's going to be any way by which I can give you something even remotely close to a sense of a proof. But what I'll do is I'll try to convey to you what exactly that statement means, what exactly this word dictionary means. So here is the thing. So you look at this group acting on the boundary, on the Riemann sphere. And when the dynamics there splits into two parts. There is a part which is called the limit set. It's basically the set of accumulation points in the Riemann sphere of an orbit of some point in O. So you look at a point O in the interior hyperbolic three space. Look at the collection of points that you get by moving it around by G. Then look at the points on the Riemann sphere towards which it accumulates. The quotient need not accumulate in general to the whole sphere, but the collection of points it accumulates to is called the limit set. So it's essentially a limiting behavior, so it's called a limit set. So in particular, for the 2, 4, 6 group that we talked about, yeah, the double torus group, it acts on it preserves the equatorial plane in this three-dimensional hyperbolic geometry. It preserves a copy of H2. So its accumulation is going to be just a round equatorial circle in the sphere. So what happens in this setup is that the intrinsic boundary, which is the two-dimensional, so you think of this group as just a two-dimensional group, its intrinsic boundary is the round circle. What is happening here is the easiest thing that can happen. From a different point of view, it's the most boring thing that can happen. It's essentially the intrinsic boundary of the hyperbolic plane, namely the circle, embeds as a round circle in S2. So that means the hyperbolic plane, I mean, this is what's called totally geodesic embedding. That means there is no extrinsic geometry at all. The intrinsic geometry captures everything. So that means when you embed it in the two sphere, the boundary, which is the intrinsic boundary, which is a circle, embeds in the two sphere, which means in particular, it's a continuous map. Yeah. So the answer to this question, if you have a hyperbolic group acting on hyperbolic three space, the thing is that the 2, 4, 6, which acts on the hyperbolic plane, the action extends to a very nice action on hyperbolic three space, and the boundary just naturally embeds. Round circle embeds as a round circle. This is the simplest kind of behavior. And now we are asking, can there be something more? Can there be something more interesting? The answer is yes. Indeed, yes. You can deform this representation slightly, and you get these fractal circles where the geometry at one scale is replicated at all scales. And so the limit set is the locus of chaotic dynamics, the limit set, which is the collection of accumulation points of the G action on the sphere. Yeah. So the limit set is, which is the collection of accumulation points that we described, is really, that's where the dynamics is the most chaotic. Yeah. What it means is that if you take any point on the limit set, you look at its orbit, it turns out to be dense in the limit set. So there is no point which is preferred. So every point is accumulated upon by an orbit of a point in the limit set. So this is where the dynamics is most chaotic. Yeah. And here, what we are asking is the following. You have this Cayley graph. What does it do? It takes a point in your group and sends it to the image, or you choose a base point, say the origin in hyperbolic 3 space, act on it by the group. So you send your group, which is an abstract algebraic element, to the image of a base point under that group action. This gives rise to an embedding. It's a priori, it just gives rise to an embedding of the vertex set of the Cayley graph, but the vertex set really captures the whole geometry. What it does is sends a group to an orbit. And what we are asking is basically, does this inclusion of Cayley graphs extend to a continuous map, yeah, between the circle boundary of G? So I'm thinking of G as a surface group. Here, a surface is something that acts on the hyperbolic plane. Its intrinsic boundary is a circle. And what we are asking is, does this action of the surface group in the hyperbolic 3 space, and in the previous slide, we had given an example, again, of a surface group, but now acting in an interesting way, not in a flat way, on the three-dimensional space, which is basically when we have deformed the circle a little bit. Yeah. And now we are asking the following. Is there a continuous map? So does this action of the group on the hyperbolic 3 space, does it extend continuously from the circle to the sphere? If this extension is continuous, if it exists, that's called a Cannon-Thurston map. Yeah. Why? Because the first non-trivial examples of this, yeah, they basically, it's a piano. What Cannon-Thurston gave was an example of a surface group acting on a hyperbolic 3 space, such that the limit set turns out to be all of the 2 sphere, which means it's a space-filling curve, a continuous map from the round circle onto the 2 sphere, which is invariant under the group action. So it's a space-filling piano curve. Yeah. Those were the first really exotic examples that Cannon-Thurston came up with, and it's what we will try to address. So basically, for arbitrary surface groups, which act discretely on the 3 space, this question basically asks, is there a Cannon-Thurston map? The answer is yes. In fact, for all finitely generated 3-dimensional Kleinian groups, Cannon-Thurston maps do exist. What is the result? It means that these limit sets, which a priori could be really horrible, yeah, they are topologically controlled. Yeah. It means basically that this continuous map, what is it? So you have a continuous map from a compact locally connected set, namely the circle, into the 2 sphere in general, not necessarily onto, and then you apply a theorem from general topology, which basically says that if you have one of these things, then the limit sets are actually locally connected. Yeah. So if you can prove, and then there's a theorem of Anderson and Maskett, which basically says that if you can prove local connectivity for surface groups, then that's enough. That's actually allows us to conclude local connectivity for all of the limit sets for all finitely generated Klein groups. But in fact, actually, it gives you much more structure theory. These Cannon-Thurston maps gives you much more structure. So the answer to Cannon and Thurston's question is really yes. Yeah, and it holds in great generality so long as your ambient space is hyperbolic free space. Now, how I said that at the very beginning that dynamics on the boundary is connected to geometry on the inside. What have we done? So far, what we have said is that the dynamics on the geometry is controlled. What we've said so far is that extrinsic geometry and the boundaries speak to each other very well. Yeah, that's the existence of the Cannon-Thurston map theorem. Now, there is another very, very deep theorem, which is due to, Minsky dwelt on this theorem for more than 15 years, and the last part of this work is joint work with Jeff Brock and Dick Canary. What they basically said, now let us look back at the quotient manifold. The quotient manifold that we were looking at, this quotient of hyperbolic 3 space by this discrete group, that's a 3-dimensional manifold. It has a certain asymptotic geometry, which means as you exit ends, there is a piece of topology that is hidden at infinity, and that's a topological piece of information. And what they proved, it's called a lamination. That asymptotic topology, it determines the geometry of M exactly. Yeah, this is what their theorem was. It's called the ending lamination theorem. Okay, and what we were able to prove is that this Cannon-Thurston map, which is purely at infinity, it recovers this lamination, this asymptotic topology exactly. What that means is that the Cannon-Thurston map, it's a continuous map. So a continuous map need not be injective. And what this theorem really says is that the points of non-injectivity capture exactly this ending lamination. It captured exactly the topology at infinity of these 3 manifolds. So now you put all of that stuff together. What do you get? Yeah. Dynamics on the limit set captured by Cannon-Thurston. Dynamics then captures exactly the asymptotic topology. Then you hit it with this hammer. That asymptotic topology determines geometry. Put these 3 statements together. This is the meaning of this blurb that I had given a few slides back, that chaotic dynamics on the boundary, in particular, the locus of chaotic dynamics, which is the limit set, along with its dynamical information, it determines this higher dimensional thing, namely the 3-dimensional hyperbolic geometry. And certainly the other way is much easier. The hyperbolic 3-dimensional geometry certainly determines the action on the limit set. Why? Because a priori, you're losing information. From 3, you're going down to 2. So the action on the inside leaves a trace on the boundary, and that captures the dynamics on the boundary. The real content of this theorem is that from this 2-dimensional piece of information, you can actually go inside. You can recover the 3-dimensional, what is happening in the 3-dimensional geometry inside. Yeah, so physicists give this all a very exotic name. They call it the holographic principle, but they have a somewhat different take on this. This is a classical conjecture of Thurston, and what it basically says is that you look at the dynamics on the boundary, in particular the chaotic dynamics. From that, you can recover some asymptotic topology of quotient manifolds. From that, you can determine the exact geometry of a 3-manifold up to isometry. So dynamics in the 2-sphere and geometry in hyperbolic 3 space determine each other completely. This is exactly the dictionary. It's a completely faithful dictionary. So I'll stop here. Thank you very much.
Thank you very much, Mahan, for a wonderful talk. I see one question on YouTube channel asking if there is a relation between hyperbolic metric space and Hilbert metric space.
Mainak, I'm
Oh,
losing.
so there's a question saying, is there a relation between hyperbolic metric space and Hilbert metric space?
What exactly? I mean, so there is a notion of a Hilbert metric. And the answer, I mean, the quick answer is, of course, yes. Yeah. I mean, there are certain convex subsets of the projective plane, which equipped with the hyperbolic with the Hilbert metric is exactly the hyperbolic three space. Yeah. Okay, so some of these questions have been addressed. Fractal, we've said what fractal is. Boundary. Could you elaborate on what you said about the holographic principle? No, I can't elaborate. I don't really know enough about it. It's basically, what does it mean? It's just some it's essentially this thing. I mean, what is a holograph supposed to be? It's supposed to be some three-dimensional information and project it onto some two-dimensional screen. And so that's what a holograph is. It's supposed to capture three-dimensional information. That's all that it's saying. Yeah. I mean, it's a fancy name for the fact that you can actually capture three-dimensional information on a two-dimensional boundary. That's all that is. Yeah. So the actual precise mathematical content is already what I've talked. It's just a name. Don't get stuck on names. Get into the content. Yeah. So this is the content is essentially this. Dynamics on the two sphere determines three-dimensional geometry.
I have a basic question, like, is every three-dimensional hyperbolic manifold a quotient of H3 by some discrete?
Minak, you are not audible enough.
Oh, sorry. Uh, I have a basic question, like, is every compact three-dimensional hyperbolic manifold quotient of H3 by a discrete?
Yeah. So if you impose in addition completeness, suppose you have a hyperbolic three manifold such that with the equipped with the metric, it is complete. Yeah. Which means basically geodesics can be extended infinitely. Then the answer is yes. Why? Because you have if you have a complete hyperbolic three manifold, then you look at its universal cover. Yeah. That's going to be locally, it's a hyperbolic just means constant curvature -1 in all sectional curvatures -1. So you pass to the universal cover, then what are you going to have? You're going to have a simply connected, complete hyperbolic manifold. And a fundamental thing from maybe a century back basically says that if you look at spaces, complete spaces of constant, simply connected complete spaces of constant curvature. +1 gives you the three sphere, 0 gives you flat Euclidean space, -1 gives you hyperbolic n space. So yes, the answer is yes. If you look at complete guys, which means basically as metric spaces, they should be complete. Then the answer is that the universal cover is three space, and so the universal cover quotiented by the discrete group gives back your manifold. So then yes, a complete hyperbolic three manifold is indeed a quotient of hyperbolic three space by a discrete group antenna.
Okay, thanks. There is one question I see on chat. Does hyperbolic geometry necessarily?
What does that mean? Hyperbolic geometry is in a higher dimension. What I have tried to illustrate in this talk is that hyperbolic geometry in n+1 dimensions reflects in a fractal at the boundary. That's the point that we have talked
Um, Sir, one question. So, like, it's like very basic. So, you said about the fundamental group of H3 mod G. So, like,
Yeah.
whenever we are taking this
Fundamental group of H3 mod G is G.
okay, yeah, like, okay. No, like, you said that it corresponds to a group of deck transformations. Like,
Correct. So if you look at the universal cover, you think of G as acting on H3. The quotient is H3 mod G. And so the deck transformation group in the universal cover is exactly the same as the fundamental group of the quotient. This is the way you go.
okay. Okay. Thanks. And sir, this the limit set what you have defined, like, does this like have any connection with the omega limit sets what we define in dynamical systems?
Yes, very
Like
much,
we,
very much so. Very much so. Yeah, it's
oh,
basically what are you doing? You're looking at a group acting on a space, and you look at a point, look at its orbit, look at the collection of points on which you have an accumulation. That's exactly what the limit set is.
okay. Yeah, thanks.
There is a question on YouTube asking uh, if we are to look at something with infinite dimensional vector space, can we still discuss any sort of projection?
Mainak, I can't hear you.
Okay, so sorry. So question on YouTube asking, for something like an infinite dimensional vector space, like say continuous functions in R, can we still discuss any sort of projection? Okay, I don't know what
I
actually
don't know
meant.
what to make of that question.
Okay.
Okay, so suppose you have an infinite dimensional vector space. See, the thing is the H3, as I said, it's basically a group. Yesterday we had talked about this. It's really a group which is SO21 is the isometry group of which it's another form of SL2R. So basically you look at three-dimensional vector space and you put a quadratic form on it. X, Y, Z is x square plus y square minus z square. So one has minus signature -1, the other two have signature +1. Yeah. So that means now you look at matrices A such that AV, AV comma AV, yeah, with respect to this inner product is the same as V comma V, yeah. Then what is the inner product? It's basically the signature form. I mean, with an indefinite form, x square plus y square minus z square, yeah. Then the group that preserves it is exactly the isometry group of the isometry group given by this continuous group SO2 comma 1. Today, what we talked about is x square plus y square plus z square minus w square. Yeah. So that's 1 comma 1 comma 1 comma minus 1 signature. Yeah. So that's SO31. That's the same thing as this, essentially the same thing as this PSL2C. So now you can look at an infinite, countably infinite dimensional vector space. And now you can put signature -1 in the first place and ones everywhere else. That's going to give you an infinite dimensional hyperbolic space, SO infinity comma 1, and that has definitely very interesting applications.
Hello, 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 hello,
Yes, we can hear
hello.
you. Please go ahead and ask your question.
Yes.
Oh, okay. May I ask two very simple question, please?
Yeah, go ahead.
Oh, okay. My first question is there any connection between hyperbolic geometry and quantum mechanical science or technology? This is the first question. And the second question is, Maharaj, if the hyperbolic space as a topological space is not connected, then how can we find the geodesic? If it is connected, then it is okay. But if it is not connected, then what about the geodesics? These are the two very simple questions,
The
Maharaj.
first question, the mathematical structure behind quantum mechanics is really operator algebras. And I mean that's how von Neumann found the mathematical underpinnings of quantum mechanics. And really, hyperbolic geometry has much more to do with the relativity aspect of things. So if you look at special relativity, where dx square plus dy square plus dz square minus dt square is your metric, that's the 3,1 space. You look at it, as I said in the previous lecture, that if you look at the unit sphere in Lorentz 2,1 space, you get the hyperbolic plane. In exactly the same way, you look at 3,1 Lorentz space and you look at the unit sphere there and you restrict the Lorentz metric there, you're going to get a different model for hyperbolic 3 space. So the connection is with relativity, not with quantum mechanics. One. Second question, we are looking, I mean, even to define a hyperbolic metric space, we needed a geodesic metric space to start off with. Yeah. Without that, the notion of geodesics does not make sense. And without that, a notion of triangle does not make sense. And therefore, a priori, for a disconnected space, a notion of a geodesic does not make sense. Yeah. So therefore, the notion of hyperbolicity will just not make sense. On the other hand, even if it is a disconnected space and any 2 points can be connected by an interval in Z. It's just the integers, that's the collection of integers. Yeah, so the vertex set of Z. Yeah. And you define it as, so what is a geodesic now? It's now a discrete geodesic, which means that the intervals are not there, but you just have a sequence of points. And then a geodesic is now regarded as an isometric embedding of an interval in Z into the space. Then even for a purely, I mean, discrete space, if you redefine your geodesic as an interval in Z embedded isometrically, then you can make the sense of a discrete geodesic precise. And with that, you can do hyperbolic geometry. Hopefully that answers both questions.
Okay, so there are some more questions on YouTube. What's a good book for surfaces, geodesics, hyperbolic geometry to start with? And
oh, very good. Very good. Good question. So as I said, hyperbolic geometry, Radcliffe's book is a good book. For surfaces and geodesics, there is a book by Docarmo, which is very good. Yeah. Docarmo, I think it's called Differential Geometry of Curves and Surfaces. That's a great book.
And there's a new question. Yesterday you mentioned that open and not, we add a dimension. Here also the dynamics of one lower dimension is related to geometry of one higher dimensional hyperbolic space. Can the geometry of knots be in some way connected to this idea of dynamics in lower dimension?
Yeah. So the thing is, what I said yesterday was not that to open a knot, we add a dimension. I said yesterday that, look, if you have a line crossing another line, so basically a rope in a flat space, and then there's another rope intersecting it, then we can remove, so there's one rope that goes over it, and you're assuming that it's all lying flat in a plane, but then there's a point of intersection. What you do is you raise the second rope a little bit, and then the intersection is gone. So this is a way, basically, knots can be drawn by their projections into the two-plane, and then you look at the overcrossing and lift that overcrossing in 3 space, and that's going to be a representation of a proper knot. Yeah. Okay. And then can the geometry of knots be in some way connected to this idea of dynamics and lower dimension? Yes, but it's going to take us very far afield, and it's not directly connected to what we've been talking about. Okay, that seems to be it, right, so far?
Okay, does anybody else want to ask a question? You can even unmute and ask it.
Yeah. Good questions, by the way.
Is it possible to give you some idea about the current interesting research trends or what?
Oh, yeah, sure. So basically, one particular topic which is of considerable current interest is that, see, the thing is, we have been looking at representations of surface groups into SL2R and SL2C in here. What are the discrete faithful representations of a surface group into SLNR or SLNC? This is something that is being right now investigated. It's called, the theory field is called higher Teichmüller theory. It's an extremely, I mean, we are actually going to organize a special semester on this topic in 2026 fall at this newly founded Lodha Mathematical Sciences Institute. So yeah, it's considerable current interest. Connects to, I mean, in fact, yeah, since Moinak is here, yeah, so Hitchin did some very fundamental work, but more from a algebraic geometry point of view around 1990. But the internal guts of these representations, the geometry of these representations was found more or less 15 years later by Laborie from a dynamical point of view, and from a more combinatorial algebraic geometric point of view by Fock and Goncharov. And that's matured over the years, and now there's a lot of work that's going on. Yeah. So you replace the target group and you get a whole bunch of things and lots of unknown questions.
Another question is from somebody: is hyperbolic spaces related to toric variety?
Toric variety. See, the point is all of mathematics is connected. So, yeah. I don't think that there is a direct connection. Toric objects are flat typically. Yeah. And hyperbolic is minus, negative. So, yeah. Typically, I mean, the quick answer should be, I mean, a natural answer, expectation would be no.